We're Team 8, and we built a vaccine transport container. I'm Noah Baird.
I'm Bryce Arnold.
My name is Daniel Scafidi.
And I'm Jake Gray. The goal of this project was to create a shipping container for vaccines to solve the issue with the cold chain, in which millions of vaccines are lost each year to freeze damage or heat damage and vibration. So the goal of this project was to create that type of container. So we had a vibration damping pneumatic component, and then we modified a refrigeration system to fit the needs of our shipping container. To construct the container, we selected aluminum extrusions to build the frame with, and we did this because of its low weight and high strength, and also the ease of working with it. In addition, we used acrylic for the paneling and for the refrigeration container, and this is because it has a low thermal conductivity, and you can also see through it, so it's easier to see what's happening inside the system.
We decided to go with the mechanical compression refrigeration system. The compressor that we use is from a Black & Decker refrigerator, and it uses R134A refrigerant. We just had to simply make a customized evaporator and condenser coil to fit our application, but we kept the design constraints and dimensions to as close as factory as we could to eliminate any variability in the cooling capacity from the factory system. The target temperature for the refrigeration system was 2 to 8 degrees Celsius because that is the average temperature that vaccines like to be safely transported at. And we were able to get the temperature of the inner chamber of the insulated container down to 7 degrees Celsius. So we did achieve our goal, but for a future design or production models, we would like to further insulate the container, either by adding more aerogel insulation or creating a better vacuum without to reach a lower temperature so we can accommodate a larger variety of vaccines that would say require a lower temperature for a safe transport.
The electrical system is used to control the pneumatic system as well as the sensors. We have a dual-core processor for inputs like the sensors and outputs, which would control these solenoids. These solenoids are used to control the pneumatic system, and we have these CO2 canisters here for the pneumatic system.
So we implemented a pneumatic system to help dampen out any vibrations that the container itself may see during transport. Those vibrations will be experienced through the gyroscope located at the lower portion of the tray itself. And from that, the microprocessor will actuate these solenoids, and these solenoids will open and close a set pressure set by our CO2 cartridges located here. And those will extend or retract our air cylinders located at the four corners of the base plate to raise, lower, tilt, or help dampen out anything that the container may be experiencing to help minimize the chance the vaccine may be broken during transport. The pneumatic and electronic systems yielded a successful result. They were able to actuate the leveling plate up and down as well as balance out any vibrations that we may foresee in this closed controlled application. But further improvements would be more physical real-world testing, as well as making the electronic system fully remote so that it can be self-powered and taken on longer journeys where power may not be available. Here's an example of the passive dampening system, how it would actually be implemented inside of a vehicle. So in transportation, there are foreseen bumps that the vehicle could encounter while the vaccines are being transported. And those applications of force would be dampened out by the pressure located inside of these cylinders to help mitigate how much the vaccines actually move, as well as the electronic system having a more accurate response based off of the output of the gyroscope.
Thank you for listening to our design presentation.
And special thanks to Dr. Tahi, Fred, Nan, Zach, Mateo, and Donald for all the help on our project.